Hello again. It's a pleasure for me to introduce our second speaker of this CAR 2022, Professor Jorge Ramírez. Jorge Ramírez Alfonsín, sorry. And as it's usual for me, I didn't make a curricular presentation. I prefer to make a frame presentation. So I met Jorge many years ago in the Math Institute of UNAM in Mexico when I was a student. And he just arrived to the institute after finishing his PhD. And a very short time later, he moved to France and we lost the contact for many years ago, for many years. But a little years ago, I don't know, 5, 6 maybe, I invite Jorge to come to Mexico to give a course in one conference that we were organizing. And Jorge immediately said yes, of course. And I think that after this, he frequently visits Mexico again for many conferences. So I really like to say, Jorge, thank you, because he's always with time and with to participate in any of our events. And moreover, I like to say that not only the math are a common interesting for Jorge and for me, we are interested to write too. So maybe someday we receive a surprise about Jorge and Rita. Okay, thank you very much, Jorge. You can start.
Thank you very much. It was it's a great pleasure being with you, and thank you very much for this occasion to share this with me. So let me share my. Let's see.
We can see the slides and we can hear you.
Oh dear. It's gone. Wait, I want to try it again. Is that okay?
It's not on full screen.
Let's see.
There it is.
Okay, perfect. Very good. Well, so it is a great pleasure for me being here with you and try to explain you a little bit what we have been doing for the last years. And it has to do with self-dual maps. And this is a joint work with Luis Montejano and Ivan Reskin. So I'm going to explain things without too much technicity. I'm going to use lots of figures and draws, and I think it's better like this, right? So we just better understand the idea instead of, looking very mysterious formulas and stuff like that. So let me start. We have a planar graph, so we're going to denote this by G. So we have planar graph G, and then we have a G star, which is a dual. And with these two fellows, we're going to introduce some other graphs that we're going to use for our purpose. So instead of give the formal definition, I'm just going to do draws. Oh dear. It blocks there. Sorry. It. Oh, there you go. Let's see. Okay, so this is graph G here, and we have the dual with a dotted line. With these two graphs, we can define the graph what we call square graph. What is this? Well, it's just a graph in which you draw G and the dual at the same time. And every time you have an edge from the dual and an edge and the corresponding edge from the primal graph, you put a vertex there. So one vertex here, one vertex here. In intersection, you put one vertex. And that gives you a graph. And this is what we call the square graph. Why it is square? Because all the faces are squares, actually. Very good. Another graph that we're going to use is the vertex face incident graph, which is a graph in which I'm going to keep the vertices like this, and I'm going to join vertices white with black vertices. So for each white vertex, I'm going to join to the black vertices corresponding to the face in which this white vertex is, right? So for each face, we have one white vertex. So this fellow is going to join to this one, to this one, to this one. And for each face, I'm going to do the same, right? So this fellow is going to be joined to this, this, and this. And this is the triangle over here. This is the other triangle. And this one is the exterior graph, right? The exterior face. So we have this graph, this is the incident graph. And we're going to need the medial graph. What we all know, it's given this graph here. We're going to put a vertex in each edge. I'm going to join two vertices, whether the two corresponding edges are consecutive in the same face. So if I put one vertex here, one vertex here, one vertex here, well, this is going to give me a triangle, right? And then I have another triangle here for this vertex here, which are these two triangles there, these two triangles there, and the rest are the exterior face. Okay? And finally, we're going to mix this graph and this graph. And it turns out that these two graphs are dual graphs. And this is it. This is the dual graph, right? So I draw in the same, at the same time, the incidence and the middle graph. And therefore, if they are dual, I can define the square of the incident graph. Just as I have done it here, well, I'm going to do it here again. For any crossing edge of the medial and the incident graph, I put one vertex, which is here, and this vertex here is here, and so on. And that's give me a square of the incidence graph, right? So I'm going to use all these graphs for all what I need. Now, what a map means. A map of a graph G, it is just the image, it's just an embedding of G into the two sphere, right? So you take your sphere and you just draw your graph into the sphere. So let me give you one example. There you go. So you have your graph, your planar graph, and this is an embedding. So for each vertex here, I'm going to choose one point in the sphere. And for every edge, joining two vertices, I'm going to put one Jordan curve joining the two corresponding points in the sphere, right? Now, the only condition is that these Jordan curves do not intersect itself or from each other, right? There are no intersections. The only way they intersect are at the ends. So for instance, this Jordan curve intersect this Jordan curve just at the end, just on one vertex. Otherwise, it is not intersection. So essentially, that is what we call an embedding. And once is embedded in the sphere, that's what we call a map. Given the map, we can define a face, right? Just as we have faces in the drawing in the plane, we also have faces in the drawing in the sphere. Essentially, what you do is take your drawing and then just delete the drawing and leave the rest. And the rest are regions, and these regions are There are no connected regions, and these regions are the faces. I think I have done, there you go. For instance, this face here corresponds to this face here in the sphere, right? Which is just a region, right? So, and therefore, just as we can make the dual of a graph in the plane, once we have a map, we can actually think about the dual of that map. There you go. You take, for instance, the red is the graph G. And then I take the dual for each region. Now I define the region in the sphere. Well, I take 1 point for each region. So you see there is this region behind, red region. I put the vertex behind there. And then I'm going to join two regions, whether they share one Jordan curve, right? And that gives me an embedding. So I have an embedding of G and G star at the same time, right? Okay. Now, I'm going to, probably I'm going to move this here, over there. Okay. This is the formal definition. This is what we are looking for. This is what we are interested in. The antipodally self-dual. What that means? It's very easy, actually. I want to embed G and G star at the same time, but they must be antipodally embedded. That means that if you have one vertex of J, which is a point in your embedding, you must have antipodally, opposite antipodally, vertex of G star of the dual. So let me give you an example. There you go. Take this embedding of K4, the red graph. This is K4, right? Everyone is joined to everyone. And then I take the dual. It's again K4. And I take this embedding, the blue one. And you see, these two embeddings are antipodally embedded. If I take one vertex, one red vertex, diametrically opposite, there is another vertex, which is a blue vertex, which is the dual. If I take this vertex here, well, the antipodally opposite is this one, right? Antipodally means that if you join actually these two vertices with a line, you are going through the origin. The antipodally embedding of this edge here, well, is this one over here, right? So it is an embedding very particular. It's not any embedding. You must verify this very strong property. You want to draw it on that way, that there are antipodally embedded. So we're interested in this, and we're interested in the second embedding that we call antipodally symmetric. Here, we want to embed the graph, and it must be antipodally with itself. There is no G, there is no G star, there is not the dual, just G. You want it to embed it in such a way that if you have one vertex in the embedding, the opposite is also a vertex of your embedding. And for the edges, the same. So let's see. Take this blue graph here. This blue is an embedding, and it is antipodally symmetric. You see this vertex here is antipodally to this vertex here. This edge here is antipodally to this edge here. This edge here, the antipodally is over here. But you see now it's just one graph. So we have two embeddings. The self-dual antipodally, so you want G and G star and the dual antipodally embedded. And you have the antipodally symmetric embedding. You just one graph, but it must be antipodally symmetric. So we're interested in these two fellows here. Well, we've been working on this for a long time. And the first question is whether we can characterize, for instance, the self-dual and when a graph is self-dual antipodally. Well, in fact, we can do it. First, let me give you one necessary condition. And I'll give you this condition because we're going to use it at the end of the talk. Now, for this necessary condition, let me recall what an automorphism group of G is, which is just the set of all these isomorphisms, all the isomorphisms of G. So you take a cycle of G, so G is a planar, take a cycle, and you say that this cycle is symmetric if there is an isomorphism, sigma, that leaves invariant the cycle, so it sends the cycle to itself, and it sends all what is in the interior of the cycle to the exterior of the cycle. In other words, you have one cycle in which everything what is inside, the graphs that you find inside, is actually the same as the graph what is outside of the cycle, right? So that's what we call a symmetric cycle. With this definition, we can give our first theorem that says that if you give me a G that is antipodally self-dual, so it admits this dual between G and G star, then the corresponding incidence graph admits a cycle, a symmetric cycle, and moreover, all symmetric cycles are of length 2 times n with n odd, right? So I certainly won't prove this, but I'll give you an example. We have seen before that K4, it is antipodally self-dual, right? We gave the embedding, which it was antipodally. So it must verify this. And indeed, it does. You see, you take the graph K4 here in blue, and then you take the incidence graph. So you take the vertices of the dual, you join the vertices to the vertices of the corresponding face. So that gives you the red graph. That's the incident graph. And the bold edges give you the cycle, which is a symmetric cycle, right? Because everything what is inside, well, is just a star, right? Is this a star here? Well, it's the same as a star, which is outside, which is with this, and given by, well, we cannot see it because of this, but there you go, with this vertex over there. Okay, so we have this condition, right? But can we do it better? Can we do better in the sense that we can we characterize the antipodally self-dual maps? The answer is yes, we can. For this is probably the more technical part of the talk. So I'll just give you an idea what we need to characterize this. Actually, we need to label. We're going to give a very specific labeling of all the vertices of G. So take G and take 2 sets, say x1, xi, and xi bar. You take these 2 sets of labels, and then you're going to label all the vertices with subsets of these 2 sets, right? But you have certainly, of course, some properties to verify. The first is that every vertex must have at most 2 labels, maybe 1 or 2, but at most 2, no more than 2. The second property is that if you give two labels to a vertex, well, these two labels are twins labels. You should have xi and xi bar. You cannot use something else. In this case, that's what we call that this vertex here is a fixed vertex in our labeling. And then this fellow says that essentially if U and V are different, then the labeling must be empty. The corresponding labeling has not elements in common. And finally, and probably the most important is this property here, which says that if you look the pre-image of this label, so this is a vertex, this is another vertex, this is a vertex we label xi, this is vertex we label xg. If these two vertices are joined by an edge, then the corresponding vertices of xi bar and xg bar, the pre-image, is also an edge of your graph. This is a quite tricky thing, right? But this is what we need. This is essentially what we need. Once we have this labeling, we can prove that a graph, give me a self-dual graph, any. Well, this self-dual graph is Antipodally if and only if the square of the incident graph admits one of these involutive labelings, but without fixed vertices. So if you manage to find this labeling without fixed vertices for the square of the incidence graph, then the graph is Antipodally, right? So it seems a little bit funny because you see Antipodally, it is a topological property, right? You need to find the proper embedding in 2 dimensions. And what this fellow says, he said, well, I'm going to give you a combinatoric criteria in order to find this topological property. It is not that bad. So we now we have this characterization. I have prepared this for you. Small example. Take G, the blue graph. You have the dual here. Then you're going to have the incidence graph. So you're going to join vertices, blue and red vertices, according with the incidence. Now this edge here is over there. Eh? I just didn't close up, but this is the same here. Then you're going to take the medial graph. So you take the medial graph. And then, you take the square of the incident graph. So what I have done here, I just take this orange graph and I put together with the medial graph, with the violet graph. And that gave me this graph here. And I found an involutive labeling of this graph. For instance, this one. And you can check that this verifies the property. And that means that these graphs are Antipodally self-dual. And of course, it's Antipodally self-dual because it admits this Antipodally self-dual embedding, right? Okay, so I think it's better like this instead of giving details of the proofs and stuff like this. But I can give details if you like. Okay, so this gives me a characterization. Well, with this, we found infinitive families of self-dual graph. For instance, what we call the n-ears. So n-ears means you take a polygon of even length, 4 or 6, for instance. You take 1 ear for each side, and then you put one vertex and join all the vertices. One vertex and join it with the peak of that ear, and that gives you the 4 ear. And you do the same for the 6 ear and 8 ear, and 8 ear, and so on. And these are the pancakes, right? The pancakes are copies of cycles of length n with n odd. This time is odd, so you have 3 or 5 or 7, whatever, and you have copies of this. You put copies of this, and you put one vertex in the middle, and you just join all the vertices on that way, right? You put here 3 copies of C5, and then put one vertex in the middle and join the vertices on that way, and that gives you a pancake. Well, we proved that this kind of graph are antipodally self-dual, and we can actually characterize when, right? For this, we need that the n must be even. If n is odd, it doesn't work. And here instead, we have that the n is odd, but for any L, for any number of copies you want to wish to put in there. Okay, so we have these infinite families. Very good. Okay. Why we are interested in this? Why you say, well, okay, that's nice. There are some connections, there are nice drawings, but why is it interesting? Well, because this notion is connected with some other notions that are very interesting for some other reasons. So let me justify a little bit this. And let me start talking with what we call the strongly involutive maps. Now, for this, take a graph, a self-dual graph, self-dual planar graph. And you're going to take a duality isomorphism. So duality isomorphism sends vertices from G to faces to G star, and faces from G to vertices to G star, but we must preserve incidence, right? So that is what we call a duality isomorphism. Okay. Given a duality isomorphism, we can define when a graph is a strongly involutive. Well, strong involutive means that take your isomorphism, you want that your isomorphism is involutive, right? That means that if you apply twice, you're going to recover exactly the same labeling that you had at your beginning. This is a very important thing. And the second is that for any vertex, the image of vertex V, that means a face, V is not one of the vertices of the corresponding face that you are sending this vertex V. It must be another face, right? So you must verify these two conditions. Now, these two conditions are very, people are looking at it because different reasons. So let me mention a few of these reasons. First, the conditions, Lovas actually introduced what he called strong self-dual polytopes. So he defined this in order to study what he called the Borsuk graphs, the chromatic number of Borsuk graphs. So he needed these strong self-dual polytopes. But if we take the definition of this geometric thing, if I just take the combinatorial part, well, actually in 3 dimensions, he defined it for any dimensions. But for the 3 dimensions, the Lovas conditions is just these combinatory things, right? So this actually is just the combinatoric part of this more general definition. So that comes from there. So there are connections between strongly involutive graphs and strong self-dual polytopes. Okay. Secondly, is because this kind of graph is very related with this conjecture, which is very, very difficult conjecture, actually. And that I give you a set of points in 3-dimensional space of size m. So there are m points. And diameter 1. that you want to prove that there are most 2m minus 2 diameters in there, right? Very, very strong conjecture. Well, it turns out that if you take a strongly involutive map or graph, that gives you actually a tree-connected graph, right? So that gives you actually polytopes in 3 dimensions. Well, these polytopes, you can use it in order to study this conjecture, right? Because these polytopes has some diameters, very specific diameters. So this connectivity, so this connection between this and this is given because this can, from this you can find some 3-dimensional polytopes, very specific 3-dimensional polytopes. Well, I'll come back to these 3-dimensional polytopes. And finally, oh there. There is a connection between this strongly involutive thing and what we call the ball polyhedra. These polyhedra are not given by a set of points and take the convex hull. It is not. It is a polyhedra constructed in a sphere. So actually, the faces are not right faces, are not planes, are part of the spheres. So people studying this kind of polyhedra, well, this kind of ball polyhedra are related with this strong involutive. Okay, so that's more or less the motivation to study this strongly. But there is another one, very important one, very, very important one, which is the constants with bodies. A constant with body is just a convex body, think in 3 dimensions, in which when you take any pair of supporting planes and you take the distance of these 2 supporting planes, they are always the same distance. No matter how your supporting planes, your parallel supporting planes are, they always have the same distance. In that case, this body is a constant width body. People, of course, like to construct this kind of bodies, right? Of course, we know one body like this, which is the sphere itself, right? You take one sphere, and no matter how you take your supporting place, you always have the diameter of the sphere. But the thing is there any other? Can we construct others? And in fact, the answer is yes, we can. And for this, we use the involutive self-dual graphs. Given an involutive self-dual graph, we can use what we call the rouleau polyhedra, which is a kind of ball polyhedra. And from this, we can construct a constant with bodies. So I'll give you an example here. For instance, this fellow here is an involutive graph. You see, I take the involution, take me this vertex to this face, this vertex to this face, this vertex to this face, and then this vertex to the opposite face. You see, you take this vertex, this is degree 4 to this square, this vertex of degree 4 to this square, this vertex of degree 4 to this square, and this vertex here on the top to this triangle over here, right? Well, I have just given you the duality isomorphism, and you can check that it's involutive. If you do it again, you come back to exactly this graph here. So this graph is self-dual involutive. And it turns out that with this, we can form this ball polyhedra, which is called rouleau polyhedra. And from this, we can construct this kind of constant width body. This is a constant width body, right? Which is beautiful, right? So in fact, this geometric property of constant width bodies, you may use graphs, something combinatorics, in order to construct them. I found very, very beautiful this connection, right? So I think I can now convince you more or less that self-dual, involutive self-dual graphs are very important. Well, we have a connection. We know that if you give me a self-dual map, this value is strongly self-involutive. If then that the graph is going to be antipodally self-dual. It's not the same class of self-dual graph. This is stronger, this implies this one, but not the other way around, right? You may ask, and this is just a corollary of one of our results, but you may ask, but can we characterize this strongly involutive graph? And the answer is yes. The answer is yes. J is a strong involutive if the incident graphs admits an involutive labeling. And now I just have to check that we do not have H's, that the ends are labeled by K and K bar, by twins. So if you are allowed to have an involutive labeling without this specific property, then it's done. Your graph is strongly involutive, which is great because that may allow you to construct some constant width bodies. Okay, so there is connection between antipodally and strongly involutive, but there is another connection, and this is I'm going to talk to you about this on another application, and I will end with this. And this application is a topological application, and it has to do with knots. Now, I don't know how strong you are with knots. I certainly not going to give you a knot course here, right? There is no time for this. So I'll give you essentially what we need with with figures, with draws. A knot is a three-dimensional curve. It's a curve which is in three-dimensional space, which is not self-intersected, and then it's closed. Once you have your knot in 3 dimensions, you have a projection into the plane, and this gives you the projection, right? And for every crossing, you must decide which part of your curve is over and which is under. That's what we call a diagram. Given a diagram, we can consider the shadow, which is, well, for the moment, ignore which part of the curve is over and which is under. You just cross. That gives you a 4 regular graph, right? You have 3 vertices, a 4 degree 3 vertices here. Because it is planar and because all the vertices are even, that means that the dual is bipartite. So you can draw with 2 colors the faces of the graph. And that's what we have done here, right? I color the faces in such a way that 2 faces sharing one edge have different colors. Okay? And I can do this again because the graph is Eulerian. You know, all the vertices are even. One I have on this, I'm going to put 1 vertex for each face, which is black face, and join 2 vertices, whether the black faces are joining, share 1 vertex here. So this black face shares 1 vertex here with this. So I take this edge here, and this edge here. And I can do the same, right? With the white vertices. I can take the white vertex here, white vertex here, and I join 2 white vertices if they share, the faces share vertices. So this exterior face shared with this interior face, 1 vertex here, here, and here. So that's why we have 3 edges here. So for 1 diagram, for 1 knot, we can have one planar graph, this planar graph here or this, as you wish. But you see, if you give me this planar graph, I am losing the information of which part is here is under and over, right? If you give me here, say, well, yeah, but then when I would like to reconstruct, I am troubled because I don't know if this goes over and this under, or this part goes over and this one under. For this, we decide to give signs according with the crossing. we have the black point of view crossing. So you say you have your black face on the top, on the bottom. You place on this way, and then you see where is the crossing. The crossing goes from the left to the top, then it's plus. If it is from right to the top, then it is minus. So for instance, here in this crossing, my black face is here, it is here. It goes from left to the top. So this is a plus. So I'm going to give a plus to this edge. So in that case, with this, I can, if you give me this corresponding signs, then I can uniquely reconstruct the knot, right? So let me give you an example how I can reconstruct. Give me any planar graph. Take signs. From this planar graph, I'm going to take the median graph. It is here. The medial graph, it is here. But this medial graph, it is 4 regular. If it is 4 regular, then I can color the faces. There you go. To color the faces. But then I can reconstruct the knot, right? Because I have the faces here and I have the sides. So I just follow the rules either from the white point of view or from the black point of view. Say I take the black point of view. So let me take this crossing here. You have one black face here, one black face here. It is minus. Minus says, well, it goes from the right to the top. So this is the right to the top. This is the over crossing, and the other is the under crossing, just on this way. And the same for any other crossing. So there's a connection from knots and graphs, right? For any planar sine graph, we can reconstruct uniquely a knot. And that's what we're going to use. Now, from knot theory, there are lots of different notions that we can study, right? Classification. So there are lots of different questions. One of the questions is whether the knot is a chiral or not. A chiral essentially means that you can take one knot to itself, but reversing the orientation of the space. Or probably you can see better on this way. You take one knot, you take another, and if you can deform continuously the first to the second without changing the orientation of the space, then these two knots, that's what we call isomorphic, right? Isotopic. So a chiral means that it is isotopic with itself. A chiral is isotopic with itself. That's it. So probably later on I can give you one example of this. There are two knots. This is straightforward. This is the first knot we have seen, which is the simplest knot that we know. A real knot, not a trivial knot, a real knot. We know that is not a chiral. And the figure 8, which is a knot we just have seen with a later example, which is a chiral. So the question is, can we say something about achirality by using our notion of antipodally, self-dual? Well, the question is, the thing is that we can do it, right? Because give me a diagram. You draw this diagram in the sphere. Now, all these points here, all the vertices have signs, and you have the two colorings of your diagram. And then with these two colorings and with the signs, you can design a knot, right? You can do it in the space, essentially following the same rules. But you see now we have this thing here. We have a map, a two-coloring sign and map, And you see this map looks very symmetric, right? Very antipodally symmetric. Well, is it true that this self-dual antipodality can tell me something? Well, the answer is yes. The answer is yes. Say, well, give me a H-sign map and suppose that the media graph is antipodally symmetric. In fact, if G is self-dual antipodally, that implies that the medial graph is antipodally symmetric. So if G is self-dual antipodally, then we have this result here, which says that, in fact, then if it is antipodally symmetric, with this okay, wait, you see, now we have this symmetric, it's antipodally symmetric here, and we can take, we can realize two things. The size of the antipodally vertices either are different or the same. And the color of each face, well, the antipodally face also has a color, right? Well, it turns out that every pair of antipodally faces are the same color or every pair are different colors. We have one of the two. And then with this, the result says, well, if it is color preserving, every pair of antipodally faces are the same. And the signs are reversing, one have one plus in one side and minus in the other. Or the contrary, the color is reversing and the sign is preserving, then the knot that we can obtain from G is a chiral. So we have, these pure combinatoric conditions to decide if a knot is a chiral, right? We don't need any more about this isotopic notion, this topological isotopic motion. We just do it by doing combinatorics. Okay, so this is it. And this is the last result. This result says, you recall this symmetric cycle we've seen before? Well, with this symmetric cycle, instead of calling it symmetric cycle, we call it a reflexive curve, because it's a little bit more than a cycle. It can be a little bit more than just a symmetric cycle, right? But essentially it says, if you give me the graph, and if the incident graphs take one symmetric cycle, preserving colors and reversing signs, or reversing colors and preserving signs, then in that case, also the graph is a chiral. Also, the notch coming from that graph is a chiral. So I give you, there you go. That is my last picture I'm going to give you. You see, I take the figure 8. Figure 8 is here. I leave here the incidence graph. And I have here my symmetric cycle of this incident graph. You see, everything what is inside is the same as what is outside. So that's the symmetric cycle. And it verifies that it is reversing color, but preserving signs. And therefore, the figure 8 is going to be a chiral. And I have done this with some other examples, so you can check. Huh? But you see, once again, we have these topological results just by doing combinatorics and doing this by exploiting this self-dual antipodality. Okay, I'm going to stop there. I want to thanks for your attention.
Okay, so thanks a lot, Jorge, for the talk. Very nice, very interesting talk. We can see this connection between both topics. So thank you very much. I don't know if there is some questions from here or from, we have to wait a little because Facebook is a little late. But if somebody has a question here. Anybody?
Me, I have one question.
Mhm.
When you go from the 4 regular planar graphs to the knots, are there 2 4 regular planar graphs that goes to the same knot?
No.
Okay.
With signs.
Sign.
Yes. No. It's uniquely.
Okay.
Yes.
Thank you. That's so nice. We don't have questions on YouTube.
Okay. And sometimes some occasion we receive questions later and then we send to the speakers.
Okay.
So thank you very much again, Jorge. It was a pleasure as always.
Oh, thank you. Thank you.
Thank you. And
Sharing
now,
all with you.
I don't know who has an announcement. Maybe Naid or Julian.
Night.
Naid, okay.
Hello,
Before to
everyone.
finish.
Hello, everyone. I invite you to see the videos and poster. In this occasion, I have three videos of the talks, of the short talks, and one video of the poster. I invite you to see in the channel of YouTube of the CAR 2022.
Okay, so thank you very much, Naid. So if nobody have any question or comment, we will see tomorrow, the same time, the same channel, different speakers, but I hope the same people. Okay, so thank you very much. See you tomorrow. Bye-bye.
Okay.
And don't forget to check the talks and videos in a continuation. Okay, thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.
Thanks.